Rustam. So the first session is going to be on applications of Dafny'. And we are lucky to have Tej Chajed for the keynote. Tej is an assistant professor in computer science at the University of Wisconsin-Madison. Before that, Tej did a postdoc at VMware Research and a PhD at MIT. And today he will tell us about the role of Dafny' in the development of DaisyNFS, a verified concurrent file system.
All right, thanks, Stefan. So, hi, my name is Tej. Today I'm going to talk about a line of research that culminated in a verified concurrent file system where the proofs largely use sequential reasoning within Dafny'. This is going to be a little bit of an unusual talk in this workshop in that about half of this proof was carried out using Coq and Perennial and Iris and this very heavyweight infrastructure, and the other half is carried out using Dafny'. And a lot of the project was about combining these two. But I'm going to talk about both pieces, and I'll talk about some interesting details about the Dafny' side of this project when I get there. My research is broadly about system software, and file systems are just one example of this kind of software. Even if you don't directly interact with these kind of systems, this is the software that powers applications on your phone, your computer, and the servers running all the cloud software that you use. A couple characteristics of system software make it particularly challenging, and are why we might want to apply verification to it. First, systems export an API that many applications use in slightly different ways. And second, they run in a complex environment that has concurrency, crashes, and they have to directly interact with devices. While testing has been hugely successful at making systems reliable, of course, we want to use verification to make them even more reliable, and to be able to cover all of the uses that an application might make, as well as all of the possibilities at execution time that come from concurrency and failures. And despite, and maybe I don't need to say this in the talk, but I think it's always worth reminding ourselves that despite their widespread importance, bugs in critical system software are still routinely discovered. And systems keep evolving. As they accumulate features, they'll also keep accumulating bugs. So my vision is to use verification to build reliable systems infrastructure. And in this talk, I'm going to focus on one piece of that, which is the file system. So whenever we do verification, we have three components. We want to take some code, a specification of what the code does, and some sort of proof that shows that the code meets the spec. And something like a proof assistant. In this case, there's going to be two proof assistants involved. One is going to be based on the Coq prover, and the other one is going to be Dafny', are going to show that the code actually meets the spec using the proof as kind of a hint. In recent years, systems verification in particular has kind of turned a corner with a number of systems verified in just the last decade. These projects have all expanded the kinds of systems that we can tackle with verification. For example, reasoning about distributed systems. In this talk, I'm going to talk about DaisyNFS, which is a verified concurrent file system. It's partly verified using this infrastructure called Perennial. It's partly verified using Dafny'. It combines PL and systems techniques to be able to stitch together the entire proof. So DaisyNFS, as the name kind of hints at, is a verified NFS server. NFS is the network file system, and NFS is a good there's a few reasons why NFS is a good target for verification. So first of all, NFS is widely used by many people, and it's widely supported with many servers and clients of this API. Which means that if we have a verified implementation, there's many clients that can use this. For example, Windows, Mac OS, and Linux all have NFS clients that can connect to an NFS server. And second, in the pursuit of good performance, NFS servers and file systems in general are sophisticated and concurrent, and which leads to a lot of bugs. And finally, because this is a file system, the bugs are particularly costly because they can lead to issues like data loss, which you just sort of can't recover from. There's no coming back if you lose your data. So DaisyNFS implements the NFS API. At a concrete level, DaisyNFS is written in Go. Part of that is directly written in Go. Part of it is written in Dafny' and then extracted to Go code. The whole thing links together, compiles to a server binary, And then clients interact with that server over the NFS protocol, which is this standard, there's an RFC for the NFS protocol that describes how you're supposed to interact with an NFS server. So why do we use Go? Go is compiled, efficient, and has very good support for concurrency. And on the Perennial side, it was good for building the tools that we needed to support the verification infrastructure. I won't talk about that in great detail, but there's good reasons why we used Go. What makes DaisyNFS special, of course, is that it has a proof. Roughly speaking, what the theorem says is that the server correctly implements the NFS protocol in a linearizable way. So every operation is going to execute atomically according to our specification of what NFS is supposed to do. And also, if the system crashes, your data is always going to be durably stored. So regardless of when the server crashes, when you restore the server, you get back all of your data. There's two core challenges in verifying a file system. The first is that the file system is generally expected to keep your data safe, even if the system crashes, right? So even if that server crashes, which might happen due to something unavoidable, like a kernel panic or a power failure, or your laptop runs out of battery. Even in this situation, after you reboot, you expect your data to still be there. And the second big challenge is concurrency in the implementation. So just as concurrent software is going to be hard to write correctly, it's also going to be hard to verify. And to illustrate both of these challenges, I'm going to give an illustrative example of a little piece of something that a file system needs to do and what goes wrong with concurrency and crashes. So this operation is the remove operation, kind of at a very high level, which deletes the file named name inside the directory pointed to by dino. This operation has three high-level steps. So first, we're going to unlink the name from the directory. And then we're going to want to free up the space that was formerly used by the file. So we're going to go look up that file, and we're going to go free all of its blocks. So there's a few things that can go wrong. So the first thing that could go wrong is that the system could fail between 1 and 2 and between 2 and 3. So I'm going to talk about both of those. So first of all, if there's a crash between steps 1 and 2, imagine that we've durably stored this unlink, but we have not gotten yet to freeing the blocks, then this crash is going to leak all of F's blocks. So after the reboot, F no longer points to these blocks, so they're kind of dangling. You can recover those eventually, but this is still not a great situation to be in. And then the second bug that I'm going to illustrate with this example, suppose we don't have a crash, we just have concurrency. And in the middle of these of steps 2 and 3, another operation comes along and it adds some additional blocks to the end of F. Because we separately got the blocks of F and then we freed them, those blocks will never be reached, the file is deleted, and again we have a resource leak. So we'll never get around to freeing those blocks unless we do some sort of global recovery. Now, in these examples, the only thing that went wrong is that we have a resource leak. But these are just meant to be illustrative. In most operations of the file system, there's multiple operations that up to multiple data structures, and crash and concurrency bugs from interrupting and issuing part of these operations can be much more serious than just leaking resources. We might return the wrong user's data if we get confused about permissions. We might lose user data permanently rather than just leaking blocks. In a verified file system, we want to systematically guarantee that none of these problems occur. So the overall approach that we take in this project is in order to scale it to something like a file system, is to separate it into two parts. The first part at the bottom is a transaction system that guarantees atomicity. This is going to essentially address these key challenges of crashes and concurrency in a generic way. And then DaisyNFS on top is going to implement the actual logic and application logic of the file system entirely using transactions. So the transaction system is going to address these key challenges, but as a result, it's going to use more heavyweight verification techniques. And on the other hand, DaisyNFS is going to enjoy sequential reasoning, and that's going to allow us to scale up verification to something this large. We need to just write a lot of code to be able to make file system actually work. And there's a careful specification for what GoTxn does to be able to bridge the two, right? Because we're combining two verification tools, we need to argue why the result is still correct, despite combining the results from two different tools. So I'm actually going to start with a specification that captures what transactions in GoTxn do, and then I'll turn to both sides of this specification. Actually, let me pause for any questions at this point. Yeah?
Oh, it's very clear.
Okay. No questions. Yeah, feel free to stop me for questions, by the way. I can dynamically tune how long the talk is. Okay, so GoTxn implements a transactional API on top of sort of a raw disk API. The caller is going to take a whole bunch of reads and writes of individual objects, say implementing the remove operation, inside begin and commit. And GoTxn is going to guarantee that that code appears to run atomically. And that's going to be with respect to both crashes. If you crash and reboot, either all of those operations are persisted or none of them are, and also with respect to other threads. Other threads observe the entire transaction or none of it. The transaction system specification starts out by saying, what behavior do we expect to have for each transaction? So this is just a spec level of what begin, write, and so on should do. This part is fairly intuitive. We kind of can easily say what read and write do. The execution of this transaction is going to be more complicated because it has intermediate steps for all of the individual reads and writes. And actually, the execution goes down all the way, when we're modeling the execution of the transaction system, read and write have a bunch of smaller atomic steps corresponding to sort of every line of the Go code. So what we want to say is that every actual execution should be allowed by the specification. This would be relatively simple if we just had sequential transactions and nothing else. But we also need to handle crashes and concurrency. So to specify crash atomicity, we now need to allow two possible specification behaviors, even for this transaction. Because we say it runs atomically, if the system crashes while running the transaction, it's possible that it becomes a no-op, right? If we crash too early, the transaction can't run. There's a lot more executions. Now we can stop at any prefix of the sequential execution. And we still want a refinement-like property where every crashing execution has a corresponding allowed specification execution. It'd be rather difficult to prove this by just directly reasoning about crashes at any point. We instead want to do something a little bit more systematic. So the way we're going to do that is we're going to write specifications for the individual operations of begin, read, write, and commit, rather than having to do some sort of consideration of all possible transactions. So I'm going to use this transaction as a running example for the talk, which copies a block that it reads from address 0 to blocks 1 and 2. The first thing that we're going to do to describe the transaction system is it's going to manipulate a logical durable disk. So this is going to correspond to this is the abstract state of the transaction system. So at this level, so the overall effect of this transaction is pretty easy to state, which is I've already given it in these abstract states. The initial state has some block V in address 0, and it's now in addresses 1 and 2. It's implied that the other addresses are not modified. So the first question that we have to ask to be able to give a crash specification to the transaction system is, what should the state of the system be between writing address 1 and writing address 2, right? So remember that the top and bottom are what the transaction system actually exposes. This intermediate state is not going to be the same thing, right? It's going to have buffered something before actually committing it at commit time. What we want to capture is that even if the system crashes in that weird intermediate state, the final logical state is going to be either the initial state or the final one. So the first idea that we introduce is to have an in-memory view of the transactional disk that represents the progress of a transaction. So the idea is that this lighter color represents what the transaction would commit if it were to commit right now. It also is what the transaction reads from if it reads its own writes. It's just like the logical durable disk, but it includes all the buffered writes from the transaction so far. And this in-memory view of the transaction allows us to specify exactly what happens at all the intermediate points of the transaction system. Finally, when we get to commit, the role of commit is to turn that logical in-memory view into something durable. So we can formalize the part about commit that I just said as a specification in Hoare logic. In this Hoare logic spec, we have a precondition saying we have some durable disk that is from the beginning of the transaction, we have some in-memory state, and whatever those two states are after commit, the durable state is going to match the in-memory view. So that's what captures the idea that we persist all of the buffered writes. So this doesn't yet capture crashes. So to do that, we wrote a new program logic called Perennial, which extends an earlier logic that only had sequential crashes. So for now, we're going to just add crash conditions to the specification, but note that eventually we're going to have a logic that also has concurrency. So actually, the idea of crash conditions is pretty simple. We're just going to add an additional postcondition called a crash condition that says what the states would be if you crash at any point during the body of tx.commit. And in this case, the way we capture atomicity of commit is that the durable state on disk is going to be either the state before this, either the durable disk that we started with, or it's going to be the current in-memory view. If we crash late enough in commit, it's going to have already persisted all the writes.
Tej, I have a question.
Yes.
I understand the specification. I guess my question is, are there commits that are so large that it's not possible to implement that specification? Because, I don't know, you've got to write gigabytes of data. How can you guarantee that you will either not write any of it or write all of it?
That is an excellent question. So the actual specification does allow commit to error, which happens if the transaction is too big. So our actual transaction system does have a limit on how big transactions are. If we want, we could extend the specification where you had to first prove that your transaction is small enough in order to guarantee that it commits. Or we could extend it with some sort of evidence on failure for why it didn't commit. Eventually, I think there are cases where, so I think the final transaction system actually, the only reason it doesn't commit is because of transactions being too big, but our specification is not precise enough to capture that. Because we're not doing a liveness proof, we're not on the hook to do that at any point, but it would still be nice to extend the proof, at least at this low level. Okay, so far I've given you a specification for what a sequential transaction system would look like, but we also want to capture concurrency. We're going to run transactions concurrently at the same time. So the transactions should still be atomic. So if we're just talking about the spec level, not yet at the implementation, when we run tx1 and tx2 in parallel, we do expect two possible behaviors at the spec level. It's allowed for the system to run those transactions in either order. There's a lot more interleavings at the implementation level because for efficiency reasons, we're not going to take a giant global lock. We're going to allow the implementations to interleave. Nonetheless, each of these should correspond to one of the two orders. And I'm just giving this as an illustrative example. This specification should hold for any combination of concurrent transactions and including multiple transactions in a row on the same thread. So concurrency means that the sequential reasoning that we did before is not going to work. At an implementation level, when we run these two things, we can say that there's a durable disk at the beginning. We can say there's some durable disk after the commit. But this is going to require us to talk about all the concurrently executing transactions at the same time. We somehow want to be able to separate reasoning about each transaction in isolation rather than having to talk about some global set. So we developed a specification that uses an idea that we call lifting to solve this problem. The key idea is that we introduce a logical notion of lifting that moves a part of the logical disk into each transaction. So that first step in this proof or in this specification is a purely logical thing that says that we're going to move ownership of the footprint of each transaction into the transaction. And now, once we have this local view, and of course, if you're familiar with separation logic, this should be quite familiar to you. We are ultimately going to use separation logic to be able to model this specification. Then within each of these threads, we can use a very similar specification to what we had before, because each transaction is only going to modify its own footprint, and implicitly it keeps everything else the same. And that means that when we run two commits, when we run commits, we can commit logically the part of the transaction modified, and then return ownership back to some global state. One thing I should say at this point is that it appears like the proof has to move ownership. It has to know ahead of time what the transaction is going to read in order to move the ownership all at once. In reality, this lifting can happen dynamically within the transaction. So you can actually acquire our system ultimately is going to acquire ownership on demand as needed. It's not going to require that you specify ahead of time what addresses your transaction wants to read. To implement this specification in, yeah, Adam.
So I'm just trying to think what this means for the programmer's view of this abstraction and how much of the implementation technique is being built into the specification. Like if you try to acquire a location that someone else has, the spec says you block or what happens there?
That's a good question. So this specification is baking in some notion of separation already. So this is an adequate specification. Okay, I should say that there's two layers to our transaction system itself. There's one layer where we assume that when you write to an address, you have exclusive ownership over it. And then the layer above that gives you exclusive ownership by acquiring locks.
So
A per address lock.
this feels like a more complex specification than the programmer would want.
Yes. Yes, so
You're suggesting it's a good trade-off to make the verification of lower levels easier?
yeah, so it's a more specific specification that takes into account exactly how we implemented this layer of the system. Not exactly, but I mean, the ownership reasoning, the ownership principles have been baked into the specification. You would need some extension if you wanted to say do something optimistic. If you wanted to have optimistic concurrency control, you need a more sophisticated specification at this level. At the end, though, we're going to say that you give the system a transaction and it runs it atomically. And it's going to be a refinement proof that says any combination of transactions is going to appear to run atomically. There's a refinement. That spec would be preserved even if you had optimistic concurrency control. But the intermediate spec that actually reasons about ownership is specific to our ownership discipline. Yeah, another question.
So you don't have concurrent read possibility?
Yes, we don't have concurrent reads. I think that could be lifted. There's nothing fundamental to the approach. It just would be more complicated. We would need to have a read-only notion of, we need to have a read-only ownership notion. That would be like lifting, where you lift only a read-only part, and then we'd have read-only locks to be able to implement that ownership. Yeah. Okay, so to be able to formally model lifting, we use separation logic. It allows us to express the disjointness between transactions in a very nice way. A key primitive is that we introduce this points to assertion within separation logic. It's going to be a custom assertion that talks about our resources. It's not going to be the traditional points to fact that talks about the heap. So we're going to introduce two types of assertions, one that allows us to capture the durable part of the view, and the other for the in-memory per transaction view. And separation logic is going to guarantee that two threads can't both have conflicting views of the same address. Now we can give a specification to commit that looks very similar to what we had before, but instead of having the whole disk and the whole in-memory and durable disks in the precondition, we're going to instead have just the part that the transaction is actually committing. So this is all the ownership that the transaction has accumulated throughout its execution up to commit. And now you can see a specification that looks very similar to what we had before, but the meaning is now that this is now a concurrent separation logic specification, and it allows other commits to run concurrently as long as they have disjoint preconditions. The specification looks pretty simple, but it hides a lot of complexity inside the implementation, where commit is running many things concurrently, and the crash condition, even though it just says this A or B, is hiding the exact moment inside commit where we actually go from giving durably all the old addresses versus all the new values. And actually that operation where we switch from the old state being durable to the new state is not even within the body of the commit code. It happens in a background thread that is constantly trying to commit new transactions. So taken together, we can give specifications to the rest of the API. Reads and writes are actually relatively simple because they're just modifying this in-memory view. A lot of the complexity is in commit. And I haven't shown here the logical operation that lifts a durable points to fact into an in-memory one. It's not actually, it's not a physical operation, it's just a logical one. So again, I'm kind of skipping one step in going from here to the next slide, where this is a separation logic spec for the individual operations. We gather all of this up into a refinement proof that shows that if you have an arbitrary set of transactions, it runs atomically when you run it through GoTxn. So every actual, yeah, Sam.
The question about the commit, the post condition. Can you, after a commit, can you write that if commit succeeded, then do something else, do something else?
You can run more transactions after a commit, yes. But you're no longer within the same transaction. So you're going to lose your transaction, and then you can start a new one.
Yes, but the new one is guaranteed. Is the new transaction guaranteed to be able to see whether the old one committed? Is there a way it can check whether?
Yeah. So the actual specification is basically from commit returns a boolean saying whether it succeeded.
Okay.
And then the post condition is like, if not okay, then you get back the old durable state, and otherwise you get this post condition.
How can this work with if the actual commit code happens in a background thread and not in the code?
Oh, commit blocks until that thread. The actual commit code does block until that thread. What I'm saying is that if you were doing a linearizability argument, this becomes difficult because the linearization point is not within the body of commit, which for some refinement techniques, that's actually tricky. Yeah. Adam.
So how does the API you expose in Go allow for planning about complex orchestrations of many threads with many transactions and something like you use protocols for Iris for modeling how things can evolve across threads?
Yeah, so the Go API consists of these operations, and you could use concurrent separation logic to stitch together multiple transactions. We tried to do this, and actually that's when we developed DaisyNFS, where we instead switched to Dafny to do the reasoning about the transactions, which greatly simplified things. What we didn't do is something where so you described orchestration between threads. So what you could actually try to do is you could try to have a combination of concurrency control between the transaction system and your own code that maybe shows that a higher level operation is atomic, even though you decided not to use transactions, a transaction for the whole thing. We didn't try to do something like that. Instead, we use some careful system design so that every operation really is a transaction. And so you get atomicity from this proof itself.
If I was just running, let's say, a bunch of transactions that are transferring money between bank accounts, classic example,
Yeah.
could I do a proof in your top layer about the bank account total sum of bank account balances always being equal across?
Yeah. Yeah, so you could actually do that proof just using the Dafny approach that I'm about to show. So you could write those transactions in Dafny. You do have to define what it means for the sum to be the same. One way that I've done this before is you can write an operation which within a transaction checks all of the bank accounts and sums them up. And you would be able to prove an invariant that this transaction always observes a constant sum.
Got it. And if we had some more complex relational example.
Same thing. I mean, yeah. You could write any invariant. I mean, the file system relies on a very complex invariant over the entire state.
Including we could use some Go state if we want.
Yep. That's exactly what the file system will have to do.
Okay.
Yep. Okay, so again, the final theorem for GoTxn is this actually fairly complicated refinement theorem that says you take an arbitrary program that uses transactions however it wants, and it gets a refinement result. All of its transactions are going to appear to run atomically, again, with respect to both concurrency and crashes. Okay, so just to summarize, the perennial logic allows us to specify this crash and concurrent behavior. I didn't talk about the proofs at all, but of course perennial also allows us to do those proofs. And the lifting specification allows us to separate out the reasoning and the specification of concurrent transactions. I think I'm a little short on time, so I'm going to say less about the body of GoTxn and how it's actually implemented. suffice it to say that there's a reasonable amount of complexity and concurrency within the body of GoTxn, within the implementation. Let me just highlight one slide here. That one of the key components of GoTxn is this write-ahead log. The write-ahead log's job is to do this core task of, I have a bunch of writes, and I want them to all happen atomically, but I also want to do this very efficiently. And there's 3 steps in the path of making that multi-write atomic. It's first buffered, then it's logged to a fixed size log, and then eventually that fixed size log, we have to free up space in the log by actually moving it to the rest of the disk. And the cool thing about this write-ahead log is that all 3 of these operations actually happen, sorry, I don't think these annotations are that helpful. Those 3 operations on this slide can happen atomically, can happen concurrently in 3 different threads. We can have a transaction writing to the buffer. We have logging and installation happening lock-free without interacting with each other. Okay, so I'm going to skip all of this and start actually talking about the Dafny part of this project. Okay, so recall that what we actually wanted at the end of the day was a verified implementation of the NFS API, which is going to use GoTxn to make the operations atomic. But we still need to actually implement all of the file system operations and logic. So the first challenge that we first have to solve is we have to formalize the NFS API. Then we need to actually leverage atomicity from GoTxn. And then finally, we actually need to fit all the operations into transactions. For the most part, this is straightforward, but there are still some things, there are some operations which could get very large, and we have to figure out how to fit those into transactions. The first question is what the specification for NFS should be. So we start with RFC 1813, which is the standard that defines NFS v3 specifically. While this document is actually pretty good in the space of RFCs, it is 130 pages of prose, and it's not really specific enough. It doesn't really cover all the cases. So the first step, kind of the standard technique, we're going to define the state of the file system first mathematically in Dafny'. It's basically going to be a map from inode numbers to some sort of file contents, and the file contents are going to be either directories or data. And then we write the specification of each operation as a relational predicate that says how the state transforms from the old state to the new state, and also what the return value is. So similar to remove, we're going to give a specification for every operation in NFS. Then the top level specification that we're going to give is a refinement theorem that says if you run NFS operations concurrently in any with any set of NFS operations concurrently, then whatever the code actually does is going to execute. It's going to appear to execute each of those operations atomically and according to those mathematical predicates that say what each operation does. And the proof is actually essentially just a composition of what we prove in GoTxn. The GoTxn proof says you can take that execution, it corresponds to a simpler execution where the transactions are atomic. And then the proof that we're going to do in Dafny' is going to show a refinement from this sequential execution to an even higher level specification where each operation is just replaced with a single predicate that says what it does. Okay, so this is what justifies why combining a refinement proof in Perennial and the Dafny' proof actually results in a correct statement for the entire system. The way we're going to prove the transactions is the standard Dafny' approach, actually. We're going to define an invariant that we're going to define some ghost state for NFS, and then an invariant that connects the state of the logical state of the transaction system to that abstract state for the whole file system. Then we'll show every operation preserves this invariant, and then the overall proof can chain together this across multiple operations. The way that the specifications are encoded is using a requires and ensures clause on every operation. In the signature, you can see that we have this requires ensures, and we ensure remove spec as well. You can see that it also has a transaction argument. And the Go code that surrounds this, that connects it to the NFS API, is going to be responsible for starting and committing that transaction. So what we know about its body, we know that its body is correct from Dafny, but then to actually run it, we need to start and stop the transaction. Now, I show the remove operation actually because it brings up an interesting implementation challenge. When we remove a file, if the file is gigabytes in size, then it actually isn't really possible to free the entire thing in one transaction. It's going to require too many writes to the disk. So in order to solve this problem and still use GoTxn, what we actually do is we split remove into multiple transactions. In Dafny, we add a method called zero free space that you can see the specification says it's a valid transaction, but it doesn't change the abstract state of the file system. All this does is it recovers any space that the inode has that it's not currently using. And then in the Go code, we separate remove into one transaction that does the actual logical remove operation, and then zero free space, which is a logical no-op, but physically recovers all of the space from the file. And I think the actual zero free space has to be run multiple times in a loop in case the first one also runs into the transaction size limits. And because this is a concurrent transaction system, we can use the Go statement to run this in a separate thread. So we don't actually have to block remove on having the free space recovered, since the caller is not going to observe the logical effects of that operation. Okay, I'm going to pause there and take questions, and then I'll go through some evaluation results. Yeah?
You're calling FS as zero free space, so directly the Dafny method, or are you calling something that wraps that in a transaction?
Something that wraps that in a transaction. I was a little bit imprecise about this whole thing. Yeah?
On the right there, is that Go code?
Yeah.
So what's the relationship between the Dafny code and the Go code, and how do you kind of, with your overall proof, what's the glue that shows that you really are the Go?
Yeah, so we are trusting that we call the operations at the right times with the right arguments in order to relate the DaisyNFS D binary to the proof. What the proof really shows is that if you write an application, any application, using all of the methods of the NFS API, then those operations are going to appear to run atomically and correctly. It's your job to figure out when you should call which operation.
Is there also some sort of, assuming you've got the mapping of data types from one language to another language?
Yeah, yeah.
The ABI aspect of the code.
Yep, so what needs to line up is that we have an axiomatic object in Dafny that says, here's what happens when you execute within a transaction. And then that axiomatic object is going to be replaced with the actual GoTxn code. And the specification for what GoTxn says every read and write and such does has to actually be a refinement of what we say in Dafny, what we promise to the Dafny code. That's the linking step that is unverified. Right? We're making an assumption about how GoTxn operations run in Dafny that needs to be met by the code. Yeah, anything else? Yeah.
More very basic question about Dafny Go connection. Are you using the Dafny transpiler
Yes.
from Dafny to Go?
Yes, yes.
You have some at least it looks syntactically similar, hopefully, Dafny and the Go output, or
Sorry, wait, we're using the actual official compiler.
sorry?
We're using the official transpiler.
Yeah, okay. So
Yeah.
you have a pretty good connection actually. It's not like a model and a different code.
Yeah, so that, okay, I was completely ignoring I completely trust Dafny on translating the actual code that we verified in Dafny. What Dafny can't really help us with is the specification that we wrote about GoTxn is just a bunch of axioms in Dafny. And there's a bunch of proof in Perennial about what GoTxn does. Those two have to be connected to each other. And those are not the same code. I mean, they can't be the same code. Yeah.
On this slide, it looks like the Go code on the right you manually wrote, but what I
Yeah.
previously thought you would be doing was to generate that Go code. from Dafny code or to
Okay.
from Dafny code?
So what's generated is fs.remove and fs.zero free space are intended to be the transpilations of each of these Dafny methods. So we do have to write wrappers.
Okay, I see. Yeah.
We also have to write a decent amount more code to actually write to implement the wire format and to connect to sockets and take TCP connections and all of that. We don't try to compile all of that from Dafny.
Okay.
I mean, I would love to do that. I don't know what that would mean. Okay, so let's see. What do I actually want to talk about? Let me just talk about a small number of evaluation results. So let me zoom out a bit and talk about some high-level results about, especially the interesting lines of code. So GoTxn is about 1,600 lines of code. So this is the code that we actually had to have pretty tricky reasoning about. Whereas DaisyNFS is 3,500 lines of Dafny, of executable Dafny code. What I want to highlight here is that GoTxn required a proof. This proof here is, the proof that we had to do for GoTxn in Perennial was 35,000 lines of code in Coq, whereas the proof for DaisyNFS is about 6,000 lines of proof in Dafny. So even though this is less code, this is kind of a good highlight of how much trickier it is to reason about crashes and concurrency compared to this top part, which is extremely productive to work on, right? And it was really only because of Dafny that we're able to scale up to all the code that we need to be able to implement an efficient and realistic file system, right? So for example, we need to have triple indirect blocks in order to have even reasonably sized files. So I've talked about some of these trusted computing-based aspects so far informally, but I do want to just detail them slightly. There's unverified code, especially the code that connects to the network protocol is all unverified. The specification for NFS is not something that's formally linked to the RFC. This is something where I'd love to have more work on, actually, of treating the NFS spec as its own object and connecting it to the RFC and to other implementations. We also trust that, so I'm going to ignore the third part, that's for GoTxn's code to be connected to its model. And then we also need to make sure that GoTxn, as specified in the Perennial proof and in Dafny, match up. I'm actually going to skip I'm going to skip most of the performance results. I want to talk about bugs instead. So we didn't find bugs in the verified parts, don't worry. But we did find bugs in the specification and in the unverified glue code. I want to talk about one interesting one. The proof assumes the caller provides a bounded inode. The reason why I want to talk about this is that Dafny has a new feature that would have basically addressed this problem. So what happened is that our Dafny code takes an inode type as an argument. An inode is a Dafny subset type that's actually guaranteed to be within the range of bounded inodes. It's guaranteed to be a valid inode number. And the Go code just passes a uint64. And this type checks in Go because those two are the same. Now, the problem is that the Dafny code is implicitly assuming that all inodes are bounded because it's assuming that you're going to pass the inode from verified code. But here we have an obligation in Go to actually meet this precondition. Now, of course, I know I should meet all the preconditions, but this was kind of a hidden precondition. There's nothing distinguishing I know saying that it's a precondition. You need to know the definition of the type. So I think now it is possible to fix this in Dafny by asking it to check all of these things dynamically, or to audit where you have preconditions. Okay, so in my -1 minute, I'm going to just briefly show some performance results. I do have -1 minute.
You have plenty of time.
I can go till 10?
Your talk started at 9:10, so you have...
I can go till 10:10. Oh, shoot. Okay, never mind. Then I will not skip this. My bad. Okay, so let me talk about the performance results then. Actually, these are good. These are important limitations as well to cover. So there are a number of features that we cover. There's also some limitations. We do have, as I said, we have triply indirect blocks to be able to have 500 gigabyte, up to 500 gigabyte files. The GoTxn proof has some limitations that I won't talk about too much since I didn't talk about Perennial. In DaisyNFS, we don't have symbolic links or access control, and we also don't have paged readdir. I think the first two are just a matter of extending the specification and the proof and the implementation a little bit more. Symbolic links are just another set of operations that have well-defined semantics. Access control is very similar. Paged readdir would be an interesting one to cover. What this means is that readdir is split into multiple non-atomic parts. There's a project called SybylFS that gives a specification for readdir for Linux. And I think it'd actually be very interesting to take that specification and port it over to here. It would still be a non-atomic specification, and so you need to cover things like the iterator being invalidated by modifications to the directory in the meantime. And this is a fundamental part of NFS, right? So you have an RPC that comes in that starts a readdir, and then you could have you could interrupt that readdir by modifying the directory in the middle. That's just a part of the network protocol. Let me do this quick demo just to show that DaisyNFS is kind of a real file system. So this is a demo recorded from my laptop a while ago now, but it's still from my laptop, where I'm going to run DaisyNFSD. Can you see this at all? Yes. Okay. And then I'm going to connect to it using the macOS NFS client. Okay. So I'm switched over to Finder, and I'm connecting to it just like I'd connect to any other NFS server. Then I drag a file in. Just for fun, I'm going to crash the file system by killing it. I promise this does not persist things. This actually crashes it. And then I run recovery, restore the file system. In the background, macOS actually transparently reconnects once it discovers the server is back online. And then we're able to open back up the file. OK, so that's an evaluation of just running the server in one example. Of course, we did a slightly more rigorous evaluation. So the first question that I've already talked about is, does Dafny reduce the proof burden? And indeed, it was actually quite significant. The other thing I should mention is the timelines for both of these. GoTxn was, let's see, maybe like a year and a half with
5 or 6.
Well, for just the GoTxn part, the infrastructure took even longer. And several of us worked on it, I think 5 or 6 authors. Whereas DaisyNFS, essentially I wrote by myself because nobody else was interested in using Dafny at the time. I'm joking, it's because it wasn't that much work. Okay, so I talked about trusting. Okay, let me talk about the testing. So we use several testing methodologies to test that DaisyNFS actually does what it's supposed to. We have unit testing for all our Dafny support libraries. I was very scared about writing any trusted code in Dafny that Dafny is using. We also ran a high-level end-to-end testing, like fsstress, CrashMonkey for testing crashes. This last one, I can't give too many details on because it was kind of a half-baked research project that Robert Morris was doing at the time. But it found a bunch of bugs in our unverified code especially. So let me talk about more of these bugs because I think actually several of them are interesting. An example of a missing spec bug that we were just missing is that create and makedir allow an empty name. They originally allowed an empty name. This is just an example of not faithfully translating every line of the RFC. So I think this is again a case where it'd be interesting to take, instead of starting with an implementation and trying to give the spec, it'd be interesting to start from the RFC and try to produce a faithful model of the RFC that's validated against a real NFS server, rather than starting from our implementation. And then to be able to join those two together. There's another one that I think is actually really interesting, which is that, again, in this code, so I already said that we're assuming a precondition that the inode number is bounded. There's another much more subtle implicit assumption here, which is that when we give a byte buffer to Dafny, Dafny is going to assume that you are not modifying anything in the state except through the transaction system, right? For this code to run atomically in Dafny, you need to not have concurrent modifications. And the reason why you don't have concurrent modifications is because the transaction system guarantees atomicity. But there is some heap memory from the buffer. And it turned out that our RPC system could take a buffer from the network, it could pass it to the right handler, it would go through this system, and then it would be passed to GoTxn, where GoTxn assumed that it had complete control over that buffer. And in the meantime, while this thing was running, and then once the commit returned, it actually came back to the RPC system, and then it reused the buffer. If you ran another RPC afterward, you could actually corrupt the state of GoTxn, because the same buffer was actually sitting in the GoTxn code as was sitting in the RPC code. So this is an example where we were assuming exclusive ownership over some sort of some state, and that exclusive ownership was not guaranteed by anything. Yeah?
Yeah, is that why? Because you're modeling, I'm not quite sure if they're both. I guess the top on the left is Dafny code, and that buffer is just a Dafny.
It's a Dafny object, yeah.
It's a Dafny object. Presumably it's just a Dafny array, so it's immutable. And
yeah, Dafny is it's assuming a sequential programming model, right? And we believe that's justified because of our atomicity proof, but this is one of the dangers of making an assumption like that. If you do have any other data, you have to actually guarantee that it also is, in some ways, we're assuming all writes go through the transaction system. Yeah. And then the Go code kind of has no way of, if we were using Rust as our surrounding language, we might have been forced to ask the question about ownership at some point. I don't think Rust completely solves any of these problems. At some level, you have to make assumptions about ownership and then actually guarantee them. Yeah?
Do you provide any support for functional correctness proof of applications built on top of this?
Oh, yeah, that's a good question. So the short answer is we don't. You could use this as a library, and then you could verify your applications. If you're actually writing an application that uses the NFS server over the standard API, then it would actually not be completely sound to use this specification, because you're not going through our API. You're going through the client system, and the client is issuing RPCs on your behalf.
Do you have a formalization of what constitutes a legal use of your?
Anything is legal. Well, what I'm saying is when you issue there's a subtle difference between you run a file system operation, you run a read and a write using the Linux API, then the Linux client translates those operations into NFS operations. The spec is about the NFS operations. It's not about the POSIX API. If you could actually write an RPC client that directly issues NFS operations, and then the spec should totally apply to that program. Or you could skip the entire NFS part and just treat this as a library that happens to look a lot like the POSIX API, as just a bunch of methods. And then you can write an application that directly interacts with the disk and gets all of these proofs.
What's the form of your theorem that says the direct RPC version is sound with respect to your library?
It's the same proof that...
You showed us some pictures and a bunch of transactions with parallel composition operators between them.
Yeah, so I mean, it's a... Yeah, so there's an on-paper proof that we have that composes the formal proof from GoTxn and kind of the obvious simulation result you get from doing Dafny proofs.
And is that with a fixed upfront set of transactions?
No. No. It is a for all programs that use transactions. Okay. Okay, yeah, so those were the 3 bugs that I wanted to talk about, yes. Okay, yeah.
So just to follow up on that, see, for our programs, they use transactions. So we have at some point a server that's perpetually handling requests.
Yes.
And the timing of these requests depends on which transactions are running at what time.
Yeah.
Logically, how do you phrase this sort of like transactions can be started at any point?
Okay, so the proof is about an arbitrary program that uses the transaction system however it wants. So it's a And then that program can also be concurrent, right? So the server is an example of such a client. What isn't connected is exactly, so the server chooses to run operations when it receives them over the network, and there's no link between the network and when it issues these operations. I mean, we're trusting that you translate and you read you connect to clients correctly and you parse these RPCs correctly. But then that's about it. After that, you get the operations that you wanted.
Is there an assumption that the program runs for a finite amount of time?
No. Yeah.
So this question might not type check, but
Okay.
I think you mentioned that you axiomatize some of like the concurrent separation logic or like atomicity requirements in Dafny, and that was
Yeah.
your. So I'm curious about like when you were writing your Dafny proofs, like did this axiomatization, like what kind of automation came freely from this axiomatization, and what kind of stuff did Dafny have?
Okay, so let me be a bit more precise about this. So we didn't have to axiomatize anything about concurrency reasoning in Dafny per se. As long as you run all of your code within a transaction, you get to use the standard program logic of Dafny. Because your code appears to run sequentially, we believe it's sound for you to reason sequentially and just follow whatever Dafny is going to do.
Okay.
It does require that you not escape the transaction system. That's really the restriction here.
Okay. So what kind of stuff were you axiomatizing? Like two transactions run like a transaction?
What we're axiomatizing is what happens for each transaction system operation.
Okay.
Like what do reads and writes do.
I see. Okay.
Yeah. It's a little bit more complicated than what I said because the transaction system allows you to read and write sub-block objects. That's the only reason why this transaction system, like, you might think it's just completely trivial. It is almost completely trivial except for the fact that we have sub-block objects.
Okay.
If it were just reading and writing whole blocks, I think like there would be almost no question about that translation. Yeah.
You can't even write concurrent programs at the Dafny level. Is that right?
No, you can't. Except for maybe very recent features, but no, you can't write a concurrent program.
So there's no kind of that. You can't even write down the concurrent programs you might want to verify in terms of some higher level app spec here, let alone carry out that proof. That would all be informal reasoning as well about the logic behind correctness at the application level.
Yes, that is correct. You would have to go down. Yeah. Okay. Yeah. That is true. This is one reason why it would be nice actually to not do this in Dafny and to do everything in Perennial. But I don't know how to reconcile these two things, right? Like you really do want the sequential reasoning, but if you want to build a taller stack, if you want to actually consume this specification from a concurrent program, it's not like you can go back and forth easily. I mean, we did go from transactions to Dafny, but that doesn't mean that we can go from Dafny back to Perennial. That's a completely different connection. Yeah.
So you had a slide where you showed bugs that you found. Did you also find bugs in the Dafny implementation you wrote while writing the proof?
Oh, all the time. Yeah.
Okay.
Yeah. I mean, the Dafny code is full of bugs. I didn't even consider those to be a problem because, I mean, it was very much incremental. Like you'd write some code and then write proofs and then in the process, of course, discover bugs and fix them. I think there's I looked at the source code recently and there is a comment to the effect of like, this is something that I don't completely understand, but the proof forced me to do it. And, you know, so I did it. I think that was a case where like it's a subtle bug that I don't fully understand that the verification caught. As far as I mean, it's also possible that there's a way to work around this and not write this code, but I think that's actually a very cool aspect of verification. We had another example of that in GoTxn where one of the undergrads on this project decided, he discovered that something was not necessary for the proof and it would improve performance, so he got rid of something that we thought was necessary. And I thought that was very cool. This is an example of where verification really helped us develop the code. Okay, so let me briefly go over performance results. I'm happy to take any more questions, but let me just give you some brief idea of what performance looks like. The setup for this evaluation, we ran on an AWS i3 bare metal instance. This is a fairly beefy machine. It has 36 cores, running at 2.3 gigahertz, and it has a very fast NVMe SSD. We ran 3 benchmark setups. The first one is a very metadata-heavy benchmark that creates and deletes constantly small 4 kilobyte files concurrently. Large file just writes a very big file. And the application benchmark here clones and compiles a C program. The first thing that we did is we compared all of these benchmarks on an in-memory disk. So this is challenging because it means we can't hide our performance behind I/O performance. And there's a single client, so we can't just parallelize our overhead across multiple threads. These are results normalized against Linux, so Linux always gets 1. DaisyNFS gets pretty good performance. It's comparable to that of Linux, but it's not quite as fast as Linux. I think even in the large file case, the DaisyNFS is just, it's a little bit slower than Linux. Linux has a slightly more sophisticated logging design. So what about concurrency? Concurrency was a major part of this work. So to do that, we took the small file benchmark and we created and deleted files across a number of clients, and we varied the number of clients. This time we run on an NVMe drive, which gives both DaisyNFS and Linux a chance to actually coalesce concurrent writes. We find DaisyNFS does get better performance as you add clients, but the performance saturates, and it hits lock contention at some point at a common lock in the write-ahead log code. Linux scales a little bit better, but it also peters out at some point. In all of these benchmarks, we do find that the CPU isn't fully utilized, the disk is not fully utilized, so it probably is lock contention for Linux as well. But it just has slightly more sophisticated locking and logging. To conclude, DaisyNFS is a verified concurrent file system. We verified it using a combination of automated and interactive theorem proving. And the transaction system enables us to combine these two very different verification approaches. One that requires us to reason about crashes and concurrency directly, and then Dafny', which allows us to do very automated sequential reasoning. Thanks, and I'm happy to take any final questions. Yeah.
So in the specification for commit in the transaction system, it seems like you were saying that on the crash it should behave like a no-op, but I also got the impression that you wanted to immediately at the point of crashing already be a no-op and not allow for some sort of recovery or repair phase after the crash?
So the crash, what I mean is it's either a no-op or it's the full operation.
Yeah, I saw that, but when the crash occurs, it'll be a no-op, right?
Up to some point, it'll be a no-op, and then...
right, in some scenario of crashes, it'll be a no-op.
Yeah.
Right, and to me, it seemed like in that scenario, in the implementation, you want it to be at the point of crashing already be a no-op instead of also allow for some program to run after the crash as sort of recovery or repair phase.
Oh, okay. So the specification is actually contingent on recovery. What it means to have this logical state is if after a crash to actually get that state, you do need to run a recovery procedure.
I see.
The recovery procedure doesn't do that much work.
Okay, because you said that there's a limit to the size of the transactions, and I thought that that limit was incurred because you don't allow such a recovery phase, but you do allow that recovery phase. And then
Yeah. The limit is actually this is just this logging design reserves a limited space for logging. It does not allow the whole disk to be used.
Right. Okay. Okay.
Yeah. And there has to be a limit because the disk is finite. So. Yeah.
Question, because I wasn't at the beginning of the talk. So Goose allows you to get some Go code and then have a cock, then transfer it to cock. I'm not sure what.
Yeah. I didn't talk about this in any detail.
Okay.
But yes, Goose is the thing that allows us to carry out these GoTxn proofs on the Go implementation. Yeah. Yeah.
So you said you use the Dafny to Go compiler to essentially plug in Dafny code into Go. So you can also go the other way around by using sort of the extern tag and plug in Go code into Dafny.
Yeah.
Is that something you considered as well?
So we had to do that to plug in the transaction system code, but I don't know how we would do that for the body of the code, right? Like, we actually want to verify the implementation of the system, so we needed it to be in Dafny in the first place. So I'm not sure how we would do anything better than this.
So the impression I got is that you had a Go implementation, and part of that you use Dafny for and plug it into your bigger Go implementation. I was thinking if you could have taken sort of the Dafny implementation as sort of primary entity and then plug in external Go code into the Dafny one.
Okay, I think this is actually just a matter of perspective. Like, you could view it like that. You could view it as there's a Dafny proof, and there's just these read, write, commit operations, and those are externally implemented. It just so happens that the proof about read, write, commit are so sophisticated that most of the proof is from that side. But you could view the Dafny code as being primary here. Or really it's unverified code and then a big chunk of Dafny and then a big chunk of verified transaction system. Right, as I think would be kind of common in a verified project, right? You're going to have some wrapper code that's unverified, that consumes the verified code.
I didn't get that.
Okay, I think okay, one more question.
Yeah.
So you've been doing work on a network file system.
Yeah.
And you can think about it as a singular entity.
Yep.
Talk about how your work would scale to, say, a distributed file system and what would be required.
Yeah, so some of my colleagues at MIT, they have continued working on this infrastructure to be able to reason about distributed systems. So I think there's two takes on this. One is implementing a distributed file system, of which there's a bunch of designs, there's a bunch of ways to do that. And then the other one is to reason about the NFS client, right? So you already have a little distributed system where you are contacting this server over the client infrastructure. And I think it would be very interesting to verify this whole combination, right? Multiple clients, even against a common server, or a distributed file system. A lot of the infrastructure for that is actually shared with concurrency, right? So the distributed system looks a lot like a big concurrent program, except that there's some memory that's inaccessible. Yeah.
In all the tools that you've used, do you have particular desires for them?
I think I have a long list of desires on every tool that I have used, which I'm happy to talk about offline.
Okay, Tej, thank you.